for the introduction. So my name is D Walther. I work at DNV. That's a Norwegian company. So I'm based in Norway. DNV stands for De Norske Veritas, or in English, the Norwegian Truth. And truth is quite related to the topic of ontology. And so it fits quite well when I talk about the industrial data ontology. Okay, I will talk about first some challenges we face in information management in industry, and how the industrial data ontology is then a proposed solution, or how it can help with that. And then I will talk about the development and standardization effort of the industrial data ontology. Okay, so industry, at least the industry that we are facing here in Norway, but it's not limited to industry in Norway. We are working a lot together with the energy industry, and that is mainly oil and gas, but also power. And that industry is transitioning away from a document-based way of working that involves a lot of manual steps in these work processes to a more automated way. This is essentially part of this ongoing digitalization effort. It has been recognized that a common digital language is needed that can be understood both by machines and by humans. And this industrial data ontology provides the semantics for such a digital language. The ontology enables the development of common digital vocabularies, and it promotes a higher degree of interoperability. The industrial data ontology, generally speaking, supports artificial intelligence. It's based on logic. And this is important for quality assurance of large, complex data sets. And it can be used for automatic verification and validation. And that last point is quite important. The implementation and the adoption of the industrial data ontology will result in improved data quality, streamlining of existing work processes, enhanced security, and more innovation. So what does that all mean? Here's an example. This picture shows sort of the current document-based way of working. You see a timeline here from left to the right, and it is over the lifetime of an asset, for example, an oil and gas production facility. And it will start by defining a need for such a facility. These consist mainly of business requirements, which then are handed over to, this design basis is handed over to create a more detailed design in several stages. They consider the purpose, the functionality, and also create engineering specifications. And a lot of documents are being created by doing that. These are things like single line diagrams, process flow diagrams, piping and instrumentation diagrams, data sheets are being created, and so on. Lots of different documents and lists of properties and parameters are being collected and compiled together. And such properties are, or such lists of properties are, for example, in form of such data sheets as shown here. There are different types of such data sheets. Here are two shown, the operating list of properties, OLOP, and the device list of properties, DLOP. And these describe operating requirements and devices that are supposed to operate in these environments. These lists of properties have also an internal structure. There are sublists and groupings going on, and they are used in different stages along the facility life cycle. For example, in procurement. So at some point, this design has been detailed and is then handed over to an engineering company or an EPC contractor, engineering, procurement, and commissioning. And that engineering company will then take this detailed design, largely copy or integrate the design information in their own systems, and then work with that. And at some point, call vendors to make quotations for different technical solutions that are needed for the facility. So they will, for example, hand out these OLOPs and DLOPs, and then a vendor can then say, okay, I have a technical solution, I have a component here that I want to sell that meets these requirements, so that needs to be checked. This fulfillment of requirements needs to be checked by the vendor and also by the engineering company, and then the engineering company can decide to go for such a component and integrate these additional properties that come with the component in their design, and so on until this facility is then being constructed, installed, and then ready to be handed over to yet another company that is the owner-operator that will operate the facility over a potential long life. And that means controlling, modifying, replacing components, maintaining the facility. And then at the end, which is not shown here, the facility may be decommissioned, taken apart, and so on. And that would be then the end of the life cycle. So this is what is going on. And along this timeline, more and more documentation is being collected and compiled. And it turns out it is rather inefficient to hand over such documentation from company to company, or even within one organization from department to department. And later, once a lot of information is being compiled, accessing relevant information becomes difficult because information is being trapped in documents or in software systems. And yeah, it is inefficient simply to work this way. This has been recognized. Some numbers have been put on that, how much money can be saved if we were to work differently. And now industry is motivated to transition to a more automated way of working. And it could look something like that. A proposed solution is to work with digital information models instead, that along the life cycle will be built up and complemented and not replicated. And there's one stable entry point or reference for the facility, and all this information is being connected and attached to that information model. And that starts with the design phase, where, and you see more and more of these yellow boxes here are compiled, and the yellow boxes stand for functional requirements. And then these light blue boxes at the end of the design phase are being filled in. These are decisions for which products are to be used. And then these purple ones, they refer to the location, for example, where something is placed and how pipes and cables are being routed through the facility. And then later actual components are being bought and put in place. And these are the dark blue boxes that then have a serial number, and that will be monitored and controlled by the operator, and then eventually replaced when their end of life takes place. So all of this is being described in this information modeling framework, where this kind of aspect thinking is taking place. So everything is seen as a system, and we can look at the system from different aspects: a function aspect, a product aspect, location, and an installed aspect. This aspect thinking comes from a standard, the ISO IEC 81346, and it is now adopted here. This information modeling framework allows to describe a system breakdown. So one would start again from general requirements, and then these requirements are taken, analyzed, and then a further more detailed design is being presented. And this can be replicated using this kind of diagrams that are being suggested by the IMF. And then these systems can be related to one another between the aspects, also within an aspect. So this is a suggested solution to collect and maintain information about assets. Now, all this requires a common digital language that is to be understood by machines and by humans. And we advocate the application of the industrial data ontology. And the value proposition is like this. The adoption of IDO would create value when it comes to common digital vocabularies. They remove essentially ambiguity. So if we have one term, it doesn't have two meanings, it has one meaning. And if we have two terms, we can understand that they actually refer to the same thing. Interoperability will improve by breaking down these silos, as I showed in the beginning. And automation and quality assurance will increase by applying artificial intelligence and in particular reasoning, because the industrial data ontology promotes reasoning. This all will impact the data quality, automation. We see efficiency gains and improved safety, and also innovation will benefit. Now, what is this industrial data ontology? It's an ontology for representing industrial data and information, for building vocabularies and managing asset models that employ reference data libraries and exploit OWL reasoning, where OWL stands for the W3C Web Ontology language. This industrial data ontology is derived from / inspired by, so it takes elements from existing standards. One is the ISO 15926 Part 2 data model, and the other one is the basic formal ontology, or short BFO, which is standardized in this ISO 21838 standard. This ISO 15926 Part 2 data model is actually related to the IES ontology that the first speaker, Alexandra, was talking about. They are using this IES ontology, and that is based, this 4D aspect thinking is rooted in this standard, in this data model. Therefore, I asked about it. Now, this industrial data ontology goes a slightly different way. It adopts a 3D way of thinking about the world, because time is inherently difficult to handle using this ontology language. And the industrial data ontology adopts or is formulated in OWL 2. It allows for precise modeling. It's a formal language that's based on description logic. It allows for automated reasoning, and everything is identified using these IRIs that are unique and dereferenceable. So you can look them up on the web if you have made that available. Currently, here on the right, we see a taxonomy, so the class hierarchy of 54 classes. There are not shown here, but in addition, 92 properties contained in the IDO ontology. This is a current state that can change depending on need. This is developed in the Norwegian energy industry, primarily oil and gas, but also applied in several other industries such as manufacturing and mining. The ontology is available at this address. So if you were to, for example, let's see, if you were to browse to this address, so you can go to the POSC-CESA Association, you can go to Reference Data Library, IDO, and you find this is the industrial data ontology. These are all the classes that you see here available in a sort of website rendering, and you can browse through and read about it. And moreover, you find there is a set of reference data already based on IDO available here as well. But this is work in progress. Alternatively, you can also interface with that using an API. This is an ontology editor protege. So if you here open from URL, and I have done that before, that's why it's stored here. If you put in this identifier that you see here on the website, then you can load the ontology programmatically into your ontology editor. And it should, of course, it jumps to my other screen. And then you have it in your ontology editor, and you can explore it, and you find the same class hierarchy in your ontology editor. And then you can explore all the properties and the other properties as well. And so on. There's plenty of information available for you to explore. So this is the industrial data ontology. How can this be used in conjunction with reference data? On the website, you have already seen a glimpse on this sort of bubbly diagram here on the right. The idea is essentially that the IDO forms the top level of this kind of a pyramid view on reference data. It provides the most general terms and categories into which everything else is being organized. So the IDO sits on the top of this pyramid, and then going further down, more and more specific, domain-specific vocabulary is being provided that is aligned with and categorized into the most general terms on the top. So this is here shown on the right. Again, this is work in progress. It is to be populated much more. At the moment, there are maybe 800 or so reference data items only. There will be hundreds and thousands more coming. You find this diagram here has these orange bubbles. Each bubble stands for an ontology module, and these blue arrows denote an import relation. So for example, this equipment ontology imports the process ontology imports the core ontology, which in turn imports the IDO ontology. The idea is that every reference data item, so every class and property in each of these ontology modules, is categorized into a general term that is provided by IDO. So a class in the unit of measure ontology would subclass one ontology, one class in the IDO ontology, and so on. There's also an ontology module for chemical entities. This is not exhaustive, again, work in progress to be complemented. And this is provided by the POSC-CESA Association under this website. Now, reference data. Since the first talk already referred indirectly to this standard, ISO 15926, this ISO 15926 standard provides a lot of reference data related to the life cycle of process plants, primarily for oil and gas production facilities. And a process plant would look something like this, very complex asset, lots of components, and requiring a lot of terminology to describe. And that terminology is provided by part 4 of this multi-part standard. And this terminology is being based on a data model that is given in part 2. Now, the industrial data ontology was meant to be part 14 of this standard, but it didn't turn out to be this way. And now we are going for a different standard number. Here's a bit of the history. So IDO development started back 15 years ago in 2008 in a joint industry project involving several companies and also academic institutions in Norway. And the industry project was called Integrated Operations in the High North. That was followed by an EU project called Optique, and then first implementations were undertaken in the EPC contractors Abels and Aker Solutions. Lots of money was invested, and they claim they have recouped that money, and they save a lot of money using this ontology and their own further development. After that, so around 2017, 2018, first standardization efforts were made, again, starting with the 15926 standard, and then later withdrawn from that standard and trying to establish the industrial data ontology as its own independent standard. So why standardization? Why is this necessary? Several companies shown here show an interest and use this industrial data ontology or its previous version. And there are these EPC contractors, there are companies in the energy domain, mainly in Norway, but also France. We have Siemens and Grundfos in the manufacturing sector. We have the University of Western Australia representing mining. We also have aerospace, automotive, and architecture, engineering, and construction represented by Eurostep, and the maritime industry. This would be DNV. All have an interest in using IDO, and they want a stable reference, mainly to secure their investments in projects. They insist on being able to use automated reasoning, and that is to support quality assurance, for example, to ensure that data models are consistent, there's no duplication, and also for automatically verifying and validating that requirements are being met. The IDO is to provide a language to integrate standards and information across industry. It's supposed to be simple and usable. Improvements have to be made to IDO. IDO is an industry-driven standard and is not finished. So improvements to the ontology still have to be made, and the quality has to be assured. For example, through the ISO process, the standardization process, and everything has to be well documented. So this is what we are doing now. And there's good news. Actually, this month, on the 5th of October, we got an ISO new project approved, and now we have a new standard number 23726 part 3. This is the envisioned number for the industrial data on ontology. It is under the ISO Technical Committee 184, Subcommittee 4 on Automation Systems and Integration Industrial Data. This is where the industrial data ontology is supposed to live. And it's envisioned to be a multi-part standard. There will be other parts. Generally, part 1 and 2 are principles and terms and definitions, but then there will also be a part 4 on scheduling. This is to be proposed next year. Scheduling is very much related to time, of course. Use cases are to be worked out, and they are probably ending up as separate parts in that multi-part standard, as well as this information modeling framework I talked about initially, that may become a separate part of that standard. Now, what is the scope? The scope is essentially to come up with such a standard document, draft international standard. It will contain definitions and explanations for all the classes and relations. They have to be improved, as I mentioned before, as well as semantic constraints may have to be added and revised. Cross-references to other standards and models have to be made. Detailed use cases worked out, and ongoing initiatives and projects have to be aligned with, and that's mainly existing work in that technical committee at ISO, as well as the Industrial Ontologies Foundry, the On the Commons project, the Arrowhead Flexible Production Value Network project, and the Industrial Digital Twin Association. So how does this standard document look like? Here you have again the taxonomy with these 54 classes, and each of these terms, as well as all the properties, are being described. There is some OWL code here in Manchester notation provided, and a simple example that shows each of these terms in use. This is being described in the document, as well as intended use of the industrial data ontology, how to model with it, and how to extend it with special purpose ontologies. For example, the semantic sensor network ontology, GeoSparkle, the time ontology, and so on, as well as detailed use cases. And then when it comes to use cases, we have already one that is pretty much worked out. This is a use case on a pump with firmware that was developed together with Siemens and Grundfos. Grundfos is the world's largest pump manufacturer in Denmark. And this use case describes a pump, temperature observations, Internet of Things, and so on. And that was submitted to the International Semantic Web Conference, ISWC, this year. Actually, next month, it takes place in Athens, and it will be presented there as an industry paper. These use cases are generally described in this way. So you have a description of the case. There will be some illustration. There are modeling diagrams, modeling considerations, as well as data all of that will be laid out and explained in detail. And that's important to do to understand how this industrial data ontology is to be used. Further use cases are envisioned or sort of confirmed. There's a use case on a pump station, use case on a pump life cycle, digital data sheets, a valve ontology, and then existing implementations of the IDO on earlier version of the IDO in ABLE. This is the material master data ontology from ABLE, and as well as a failure mode and effects analysis, FMEA. Both of them have already been reported on in the literature. So these use cases are now presented here as being part of the standard document. They may become extra parts, as I mentioned before. You can get hold of these documents here. So you go to the PostGISA Association site, you click on Reference Data Library IDO, and there you find a description of the ISO new project. When you click on it, you get the text and a lot of explanation if you're interested, as well as the working draft of the standard, which is quite comprehensive, and well, it's quite a read, over 100 pages or so, with lots and lots of details. Okay, I think I'm ready to conclude. So I was talking about the industrial data ontology, an ontology for representing industrial data and information, for building vocabularies, managing asset models that employ reference data libraries and that exploit OWL reasoning. It's time to engage in an international community and to contribute to the development of IDO. So comments, feedback are very welcome. It's an industry-driven standard. Nothing is set in stone so far. So if you have a use case, if you have suggestions for changes, bring your use case forward and be part of the community. Here on the right, I list a number of references that you may find useful. Yeah, thank you.